I guess I'm going to go through this here pretty quick, but if I forget something or if something's not clear, you know, please shout out. The main proposition that I want to put forward is that colonizing the galaxy is just simply, in the overall scheme of things, not that hard. You need a few key technologies, the will to expand, no opposition, and time. I'm going to address the first and the last. I'm not really going to address the two middle ones. Let's take a minute and talk about the Milky Way Galaxy. We're in a barred spiral galaxy. I think that's the current thinking. Right, Greg? Diameter 100,000 light years. You know, pretty big. Thickness of the disk, 2,300 to 2,600 light years. Thickness of the bulge, 16,000 light years. You know, we have some gas and dust scattered throughout the galaxy. 200 billion star systems, I think, is the current estimate. And the age of the oldest star, 13.2 billion years. So that's a pretty good size number. The galaxy can be divided into three parts: the bulge, the disk, and the halo. I've got a galaxy, and I'll describe each later. It's important to keep in mind the concept of population 1 and population 2. Population 1 are younger stars. They have a good distribution of the kind of elements that we're used to seeing, you know, iron, oxygen. Population 2 are metal poor. They tend to have mostly hydrogen and helium, very little in the way of anything above that. So if you motor into a star system that's essentially a population 2 star, then the only thing you have to work with constitutes the hydrogen and helium, and not much else, then you're pretty much in trouble. So we have to be careful when we go into a population 2 star, because that just may be very difficult to colonize. The bulge is this center region right here. It's got as has been mentioned before, it's got a supermassive black hole in the middle. The star density in that region is very, very high. And a lot of these stars are population 2. So it's questionable whether we're going to be able to colonize the center of the galaxy or not. There are probably some population 1 stars, and we're just going to have to wait and see what we got once we get there. The disk is this region here, 100,000 light years in diameter, and it's composed mainly of population 1 stars, and that's where we live, in the disk. So, you know, the disk is good ground to colonize. The halo is a sphere around the bulge. And it's mainly population 2 stars, and the density is very, very thin. So again, it's going to be hard to colonize the halo. Some of the critical technologies we need, you know, I keep using we, but really any race is going to need to colonize a galaxy is cheap, dependable access to space. If it costs $10,000 a kilogram to get in orbit, we're not going anywhere except, you know, send out a few probes and watch TV. Another thing we're going to need is the ability to exploit resources in space. We're going to have to be able to mine asteroids, comets, moons, gas giants for their resources. We're going to have space-based industries that can take these resources and turn them into useful products, you know, like mirrors, big structures, ships. We need a cheap concentrated energy source. We talked about cheap antimatter. And Jim has some interesting possibilities with that. I'm kind of intrigued. Fusion, you know, some kind of mass energy conversion. Because once you get out beyond the orbit of Mars, it's going to be hard to depend on the solar. I'm also going to assume that we have available the ability to take a ship boosted up to 0.1 C, no faster, 0.1 C, motor on over to a target, and then decelerate so that we match velocities with our target. We're going to need to have an ecology that's stable over time, you know, a closed ecology, good recycling. We're going to need the ability to build space settlements, you know, the L5 society, the O'Neill colonies. We're going to need to be able to build those. So just, you know, take a minute and kind of think about these technologies. You know, we don't have them now, but is it conceivable we could have them within 100 or 200 years? And I think for the most part, yes. Okay, the kind of technology I'm not assuming, you know, any kind of FTL communications or travel, you know, the fancy gravity plates, nanotechnology, force fields, transporters. Sure would be nice to have transporters, but cloning, suspended animation, you know, that sure would be nice, but it looks like, you know, that's not in the cards for us minerals, big minerals. No kind of alien technology. AI, I'm assuming that for some reason we can't build it. We'll have expert systems, we'll have fast computers, but, you know, they won't be self-aware. That's the assumption that I'm making. Werner Vinci's, the singularity doesn't happen for some reason. And I guess I make that assumption because it's hard to see what occurs after the singularity. By definition, yeah. Some difficult assumptions is humanity manages not to destroy itself. One of the assumptions that I made was that we had cheap concentrated energy sources with a little bit of tweaking, you know, that usually can be converted into a weapon of mass destruction. And if we have lots of those laying around, how does humanity exist or coexist with that kind of technology? And the assumption that humanity does not fall back into the low-tech subsistence existence. And I guess the threat of doing that is because we've used up most of the easily mineable resources. You know, if we fall into a subsistence role, it's going to be very hard to climb out again. A stable political system able to commit significant resources to difficult long-term projects. You know, looking at what's happening in Washington today, I'm not real optimistic, but you know, somehow we're going to have to come up with a political system that works. Let's take a minute and talk about colony ships. Assumptions have consequences. And you're not going to have any kind of gravity magic. The only way you're going to get gravity is to spin it up. No suspended animation, we talked about that. And it seems like humans need gravity. If you put humans in zero-G environments, they lose bone mass, they lose muscle mass, they're not very healthy. So the assumption is that you're going to need gravity. You know, basic physics, if you take a structure and you spin it up to 1 RPM, which if you're looking at most people, that's what you're going to have. Nothing else. You can't spin it faster, or you know, motion sickness kicks in for a lot of folks. But you need a radius of close to 900 meters. And as Robert talked about, the bigger the structure, the higher the stress, the more costly it is to build. But if you go to 2 RPM, which a lot of people can endure over a long period of time, the radius of that structure is 225 meters, which you know is doable. Thus, the ships we're going to build to carry colonists to other systems, because of these assumptions, is going to have to be a minimum of 450 meters in diameter. Given some thought to what the crew and cargo unit of such a ship would look like, you know, put together a few assumptions here. This number is pretty well fixed. This thing here is a sphere. You cut it in half, you stick both ends onto a right circular cylinder, and you end up with this shape. Then you spin it at 2 RPM, and if you're standing on the bottom here, you'll see 1 gravity. And as you climb higher, you know, gravity goes down a little bit, but you can run around and get your exercise under a 1G field. Now, this center section, I'm assuming, is going to be the cargo area. And it's open to vacuum, but it's protected from space radiation. Interstellar space, what is that, 2-3 degrees Kelvin? It's pretty cold. But because this is going to be a habitable area, you know, it's going to be nice and warm, and that means the cargo space is going to be nice and warm. If you take a machine and you stick it in interstellar space, it's exposed to radiation and zero G and very cold temperatures. Over time, it may not function very well. So I'm thinking this is what the colony ship, the crew of the cargo section is going to look like. You know, this number is fixed. This number is just an assumption that I've put together. So, playing around with the structure, if the outer hull is 3 inches of titanium, you know, it'll withstand pressure and you know, you have a nice safety factor. Main deck, you know, the bottom deck, the outer portion of the cylinder, you'll have a 1 gravity. And if you raise the ceiling 12 meters, you'll have a nice big space. And in order for radiation shielding, I would suggest putting 2 or 3 meters of dirt in there, and that gives you a nice little garden to play with, along with radiation shielding. And then above that, you have 21 decks, each 3 meters high, and that turns out to be, you know, similar to that picture that I showed earlier. The ship's hull is 42 million cubic meters. An ocean ship has a hold, but our colony ship may have a hold. And I'm assuming 500 to 1,000 crew. And if you add up all the mass, you end up with 1.5 million metric tons just for the structure. And then its class aircraft carrier is 110,000 tons, to give you some idea. And then if you add, say, 2.5 million metric tons of people of cargo, the crew and cargo section is going to be 4 million metric tons. You know, so this is not a small ship. This is going to be a good-sized effort. Again, the assumption is that we have a drive that will allow us to get up to 0.1 C, which means if we're going to go, you know, to the nearest star, it's 40, 50 years before we get there. If you go to a star 10 light years away, it's going to be a 100-year journey. So it's entirely possible that humans would spend their whole lives in this confines of the arc. So these are some of the features that you know, most people would expect to see. Okay, I think this is what the colony ship would look like as it departs Earth. I'm not making assumptions about what kind of drive we have, therefore I can't really make assumptions about how much fuel and mass we're going to need. So just imagine that the fuel tanks are variables. They could be smaller or bigger. You know, this is the crew and cargo unit. This is a sand shield. If you run into a grain of sand going 0.1 C, it's got the kinetic energy of, you know, X number of pounds of TNT. So you want a sand shield out front. This fuel tank is for deceleration, acceleration. This is the motor. You always seem to have waste heat. Thermodynamics always gets you. So yeah, you'll be dumping heat as you run up. This is what it looks like in the coast mode. The empty acceleration tank has been cut out. You know, the raw materials are now inside, being used for various purposes. Some of the tank is also being used to supplement the sand shield. And this is the way the ship is going to coast. Earth is this way, destination is this way. And here we can put up a little dish, because just because you're a colonist and you're 3 or 4 or 5 light years away from Earth doesn't mean you shouldn't be able to get HBO and email and computer software upgrades. And Claudio came up with a good system, you know, using your gravitational lensing system, we can maintain contact with the ship for what, 8 to 10 light years?
Yes.
Okay, well, HBO is an important amenity.
You know, the customer service wouldn't be any worse.
That's very true. Okay, here's what the ship is going to look like, I think, once it arrives at its destination. You know, we've discarded the sand shields, that's gone. The fuel tank is empty. We probably dumped a lot of excess mass that we didn't need before we decelerated. And the first order of business is going to be to rendezvous with something like this, a nice juicy asteroid or maybe a comet somewhere, because we need to replenish, you know, water, air, oxygen, raw materials.
Capitalize it.
Well, harvest the asteroid. Harvest the asteroid. Yeah, deploy asteroid, moon, comet mining equipment, because we need to harvest the asteroid or the comet. Replenish fuel, oxygen, metals, organics. Send out probes to the other bodies within the star system. We'll have some idea of what we're dealing with, but there's a lot we won't know. Identify locations of the first settlements, where we're going to be mining from, where are the industrial facilities going to go, and of course, you know, this communications link goes two ways. So we're going to be sending information back to Earth as Earth continues to send us computer upgrades and HBO. At that point, we begin to grow the colony. You know, we talked about the information flow, you know, to and from the mother world. I'm thinking that, you know, occasional care packages would be very useful. And, you know, Greg talked about laser launch or solar sails. Well, if we build a laser at the destination, maybe we can use that to send and receive care packages. You know, these would be unmanned cargo. The colony ship is converted into the first space settlement. You know, we develop shipping to move around the solar system, to establish mining and industry facilities, industrial facilities, and the magic of compound growth. In 500 years, starting with 1,000 people, even if the growth is only 1% annually, we end up with 145,000 people. If it's 2% annually, it's 20 million. If it's 3%, it's 2.6 billion. So that interest rate on your CD matters. Typical colony timeline. Okay. Year 20, exploration complete. Year 50, you know, we have laser launch system complete so we can receive care packages. Year 100, mining and space-based manufacturing well established. Year 200, we have space settlements. Year 500, we send out other colony ships. In year 1,000, we're ready to move into our first shell world. Okay, first colonies, you know, this is just a list of nearby star systems. We're running out of time here, so the important thing to realize is, you know, we have 12 star systems within 11 light years of the sun, 10 class M stars, you know, small red dwarfs, 2 class K stars, 1 class G, 1 class A, Sirius, and it's got a white dwarf with it. 3 are binary systems, probably more. And of course, you know, they're brown dwarfs scattered around. M-class stars, there are a lot of them. 76% of all the stars out there are M-class. They can have planets. Compared to Sol, the largest of them is half the mass, half the diameter, 6% is bright, and the light they put out is red. They have no habitable zone. They seem to have lots of sunspots. Flares are fairly common. Flares indicate a high radiation flux. But shell worlds offer solutions to those problems. You can build them anywhere. You have a nice radiation shield. You may have a big heating bill, but you can build them anywhere. Relativity considerations, there are some, but they're fairly minor. And here's what I think an expanding star empire would look like. The Mother World sends out colonies. They send out colonies. They send out colonies. Now, each one of these black lines represents a communication link under 10 light years. It's going to be high bandwidth, two-way communications, known protocols. And so the question for the SETI experts out there is, could you detect such a system easily? This galactic internet, or is it, for users only? Okay, here's another view of our galaxy. The sun is here. As this globe of colonies expands, it'll be a sphere until it hits limits. It'll hit the top of the disk, the bottom of the disk, the edge of the galaxy. At that point, you can't go any further. So you expand in all directions. The long hole in the tent is to get over here, assuming you can't go through the center bulge. And I'll carefully scale this off, and that's about 80,000 light years. So 80,000 light years, assuming that each jump is only 10 light years, gives you 8,000 jumps to get to the far edge of the galaxy. Assume 500-year colony development before it can send out its colony ships. Assume a 100-year trip, that's 600 years per jump, times 8,000 jumps, gives you about 5 million years. Okay, that's how much time you need to colonize the galaxy, given these fairly modest assumptions. 5 million years seems like a long time. But imagine that the dinosaurs, rather than going extinct, had started colonizing the galaxy. Well, their colony ships would have reached the far end, or the far edge of the galaxy, some 60 million years ago. So the question is, if the dinosaurs could have done it, if we can probably do it in 100 years or so, then how come no one has done it? How come we're not detecting signs of any kind of galactic internet? And that's the lead-in for Stephanie's panel.
And Fred.
But lifeless barren worlds around distant stars represent to the colonists who visit them worlds of possibility. So colonizing the galaxy is not that hard. I guess questions at this point? Yes?
Do you have any sense of whether or not you can get enough genetic diversity in 1,000 people to have a viable population to get to one point, grow into another 3 billion people? Is there any studies or works that indicate how many people you really have to have for viable?
And the answer is yes. There are examples of that. Also, you may have 1,000 people, but you probably have sperm banks and cell banks, for millions of other people. So it's not limited to the 1,000 people you start off with.
For that first foray, you still have a huge psychological problem with the art.
Yeah.
And there have been a number of science fiction books that talk about generational shifts and the advances they go through and deterioration of the civilization. They get to the point where they don't even know that they're half of them don't even realize where they are or what's going on.
Yeah, I've read the stories, and that's why I'm limiting the jumps to no more than 10 or 11 light years. At point 1C, that means the journey is 100 years. It's expected that within a century, human lifespan will be probably 125 years. So even at the furthest jump, there will be some old guy at that point who is on Earth. So hopefully you won't forget the generation shift.
How do you stop the population?
Well,
Before you get there.
it may not be a free democratic society. It probably won't be. Greg.
Yeah, first of all, it's a great paper. This is one of those things I've spent most of my life researching, and fabulous to see lots of people getting involved in it in the year. A couple of comments. First of all, M stars do have habitable zones, and the first planets in or very close to a habitable zone of a neighboring star were discovered at one of the Gliese stars within 16.5 light years, which is a red dwarf.
Yeah. To answer that, I was going by Dole's book.
Okay, I know.
And he doesn't, yeah, he says that.
He's early. He's
Okay, so he's all watched out. Okay, so you could have habitable planets around stars. Yeah,
it's like
okay.
so much has been made largely obsolete by the post-1995 boom in planet population. And his book was in many ways very conservative. Another thing is there was a Belgian guy in the mid-'80s who wrote a wonderful paper in JBIS. And his estimate is people on these colony ships would probably not colonize. They would stop, they might explore, they'd be provisioned. They'd stay in their colony ships because you look at a habitable planet, all those viruses and germs, etc. Why deal with it? And the last thing, I think the main reason we don't see galactic colonization is stellar population. The fact, as you mentioned very nicely, 75 or 80% of the stars are red dwarfs. Now, if this is, and I think that is why any attempt to colonize the entire galaxy is going to peter out after a few jumps. If they'll be using most likely either some form of nuclear or some form of solar power. If they're using nuclear, the only way they're going to continue from one jump to another is they would need a very large high-tech population base. It's no accident that America has a nuclear technology, Fiji doesn't. And they would need an incentive to move forward. But if your star is going to remain stable for 1 trillion years, you don't have a lot of wars, you can move asteroids and comets around, maybe you don't move. Now, if they're using solar power ships, of course, a red dwarf has much less luminosity, and a trip of, let's say, 1,000 years duration becomes a 10,000-year trip. They're probably not going to move there since they don't have to. So I would suspect after a few jumps, any attempt to colonize the entire galaxy with technology that we can imagine is going to peter out.
Well, my answer to that would be, after a few jumps, you've got the program down. You know how to colonize red dwarfs.
But then you're assuming that a society doesn't change. You're assuming that you've constructed something and the sociology doesn't change, and they're going to wish to continue this.
Chair, as we request this debate continue outside.
Yeah.
And then to go on to our next speaker, if that's okay. Very good. Thanks, Ken.